Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. It is great to have you. If you're a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. Now, you can also find a link in the description below to all of my playlists, which at this point there are 19 of. It's basically a table of contents. And of course, please hit subscribe and click the bell notification if you haven't already. So now that we are introduced, let's go ahead and get started. So this video is the next in our series on non-parametric methods or non-parametric statistics. Now, earlier in this playlist, we learned about something called the sign test. We also learned about something called the rank sum test. So the Wilcoxon Signed Rank Test is sort of a combination of both of those. Now, what makes the Wilcoxon Signed Rank Test a bit different than what we did before is that this is a paired test. So we're measuring the same thing twice. So think of it as maybe we're measuring the weight of people when they go on a diet. You'll see this in commercials all the time. So person A weighed this when they started, and then they weighed this when they ended. Or maybe like a pre-test, post-test, or something along those lines. So the Wilcoxon Signed Rank Test is a pairwise test where we look for changes or differences between those two measures. So what we will do in this video is first go over the basic concepts, and then we'll go into Excel, and I'll show you the mechanics of how it's actually calculated. Now, one small warning/note is that there is a lot of notation in this video, so there are many subscripts and superscripts that denote specific things, but just follow along, you'll kind of see what everything means, and don't get confused over those. So first, a little bit of background. So comparing two matched samples using a parametric test would lead us to use a matched sample t-test. So you remember in earlier statistics, we had a case maybe where we had a pre-test and post-test, like for exam scores, or like I said before, we had some sort of treatment. Maybe there was training method A for each employee, and then we did training method B for each employee, the same employees, and then we analyzed how those changed between methods A and B. So that was a matched sample t-test. Now in that case, we would test, most of the time, if the mean difference between the matched pairs is 0. So the mean difference, d bar, equals 0. So think about it. Let's say we did have that employee training case. So we had 20 employees, and then we had training method A, and we measured their performance on some activity. And then the same 20 employees, we then had training method B, and then we measured the same 20 employees on their performance after measure B. In that case, what we will test is the difference between methods A and B actually 0. And of course, if our test tells us that it's likely not 0, we would reject our null hypothesis, because in that case, our null hypothesis is that the difference is 0 or that there was no change. Now, the assumption, however, in that parametric matched sample t-test is that each population is normally distributed. Now, the Wilcoxon Signed Rank Test allows us to compare two populations that violate the assumption of normality. The only requirement is that the distribution of differences is symmetrical, not necessarily normally distributed. So we can think of the Wilcoxon Signed Rank Test as the non-parametric version of the matched sample t-test. And instead of using the actual data values, we're going to be looking at the ranks of the differences, and we'll see how that works as we go. So here is an example that hits close to home: YouTube A/B testing. So Chloe is an up-and-coming YouTube creator from Perth, Australia. She is looking to increase engagement on her channel by improving click-through rate, what's called CTR. A common method to increase CTR is by using quality video thumbnails. So using a third-party tool, Chloe performs a 72-hour A/B test on 25 videos using two thumbnail styles, one with a selfie photo or her face on it, and one with no selfie photo, like mine. The tool alternates A, B, A, B as the videos are served up. Chloe then downloads the data on how many clicks each thumbnail received per video. So what we have here is a classic A/B test. In this case, we are testing thumbnails on videos that is being served up to the user, and we're seeing which one is clicked most often, or if there's any difference between thumbnail A and thumbnail B. So it might look like this. So the first video, the one with the selfie thumbnail, may have 329 clicks. The one with no selfie has 329 clicks also. Video 2 has 352 clicks for the selfie, 349 clicks for no selfie, and then so on and so forth. So you can see how our data is set up. Now it's a paired test. So video 1 is getting A and B. It's the same video. Same thing for video 2, 3, 4, 5, and so on and so forth. So this is the classic case where instead of using a paired sample t-test, we're going to use the Wilcoxon Signed Rank Test. So how does this work step by step? Number 1, we place our matched samples into 2 columns. Number 2, in a third column, we subtract column 2 from column 1 to obtain differences. So the difference between the 2 columns with the 2 measurements. 3, in a fourth column, take the absolute value of each difference in column 3. This is called the absolute difference. 4, look for any differences of 0. Those will not be used in the Wilcoxon Signed Rank Test, so we would eliminate those. 5, we rank the absolute differences from smallest to largest. Any tied ranks are averaged. So we take those absolute differences and then we rank them. If there are any ties, we use the rank.avg function in Excel, and you'll see that when we go ahead and do the problem in Excel. Number 6, record or note any ranks from negative differences as negative ranks in column 4. So this is really the important part. This and the next step are sort of the meat of the Wilcoxon Signed Rank Test. So we have our absolute differences. Of course, they're all positive because they're the absolute differences. But in that column of absolute differences, we're going to sort of note which ones were from negative differences when we first did the subtraction in the first couple steps. And we're also going to record or note any ranks from positive differences in this fifth column. So we're taking the absolute differences and noting which of those absolute differences were originally negative differences and which were originally positive differences. Then we're going to add up the positive signed ranks, which is denoted with T+. We will calculate the mean and standard deviation from the sampling distribution. So we will use T+, we will use the mean and the standard deviation to actually find a z-score. So we calculate the z-statistic and find its p-value, and then of course, based off the p-value, we can reject or fail to reject our null hypothesis. So what is the sampling distribution? So for the mean, it's denoted with mu sub t plus. So what we're saying here is that if the ranks were evenly distributed, positive and negative, this is what we'd expect the mean to be. And that is denoted with this fraction. In the numerator, we have n, which is our sample size, times the quantity of n plus 1, all over 4. And that is the mean of our sampling distribution. Standard deviation is sigma sub t plus, and that is denoted by as the square root. In the numerator, we have n times n plus 1 quantity times 2n plus 1 quantity. So we just put n in where those n's are, all divided by 24 and take the square root. So that is our standard deviation from the sampling distribution. Now, of course, n is the sample size once any differences of 0 are removed. That's very important to note. So what we can do is we can use this sampling distribution, and we can use what's called the normal approximation for sample sizes of about 20 or larger. Remember, non-parametric statistics are discrete measures. They're discrete, not continuous. However, if the sample sizes are large enough, we can approximate the continuous distributions from the discrete data if the samples are large enough. And we talked about that in previous videos in this playlist as well. So the test statistic and the probability. So first we ask, what is mu sub t plus, which again is the mean of our sampling distribution if the positive and negatives in the ranks were evenly balanced. So is t plus in the upper tail or the lower tail of the sampling distribution relative to mu sub t plus? So is t plus above mu sub t plus or below mu sub t plus? So if t plus test statistic is in the upper tail, this is the way we find the probability. So the probability is z is greater than or equal to, in the numerator we have t plus minus mu sub t plus divided by sigma sub t plus. That is just a z-score. This is the same formula, same basic formula structure for every z-score we have ever calculated in statistics. We have our value of t plus minus the mean divided by the standard deviation. That is the textbook definition of a z-score. If t plus is in the lower tail, we just change the sign. So in that case, it's z less than or equal to t plus minus mu sub t plus all divided by sigma sub t plus. Now we do have to apply what's called the continuity correction factor to t plus. Now, I should have put a little star here because in some textbooks, they will have you apply this continuity correction factor. In some textbooks, they will not. In some software, it will apply it by default. In some software, it will not. So you just have to be cognizant of what your professor or textbook is asking you to do and what your software is actually doing. Because you could use a software that doesn't do it when your textbook does want you to do it, and you'll get different answers. So just to reiterate very quickly, the continuity correction factor is just something we have to apply to our t plus because, again, it is a discrete statistic and we're actually using a continuous distribution. I talked about the continuity correction factor in previous videos, but you can go look that up and kind of see how it works. It's not very difficult, and you'll see how it works in this problem. Then we double the probability in the tail to make it two-tailed. So the probabilities we see here on the left and right are just for the upper or lower tail section. And if we're doing a two-tailed test, we have to double that to make sure we get the other tail that we didn't calculate. Okay, so here we are in Excel. Let's go ahead and calculate the Wilcoxon Signed Rank Test. So we can see that in column A, we have our 25 videos, Chloe's 25 videos. In column B, we have the clicks for the selfie version. In column C, we have the clicks for the no selfie version. Now, I am going to work pretty quickly through this problem, but you can download the file, follow along, and pause at your leisure if you would like to. All right, so the first thing we need to do is find the difference between these two measures for each video. So, equals B minus column C. Easy. So because we have this set up as a table, it's going to go ahead and calculate all those differences all the way down for us, which is nice. Okay. So in column E, we need the absolute value of those differences. So equals ABS, that's absolute value. And then we need the cell next to it, close, enter. So now we can see that we have the absolute value of all the differences in column D. Now the first thing we need to do is look for any differences that are zero. And I can see down here in row 21, we have zeros. For the sake, we could do an Excel formula to automate this, but for the sake of this example, I'm just going to delete them. Okay. Next thing we need to do in column F is rank our differences, our absolute differences. So we're going to use the rank.avg function. So equals rank.avg right there. So we need the number we want to rank, which is right next to it in column E, comma. Then we need the reference or the array we want to rank that against. So that's everything in column E. Close it. And then we want ascending. So 1 for ascending, close, and enter. So now we have our ranked differences, or our ranked absolute differences, to be more specific. I'm going to go ahead and delete this NA down here where we had the zeros. Okay, so now we need to separate out our negative and positive ranks. So what we're doing is we're going to look at our rank differences here in column F, and then we're going to look at the original subtraction here in column D. Now, if this difference in column D is negative, we're going to put the rank difference in column G. If it's positive, say like we have here in D4, then we'll put that rank difference in positive. So basically, we're using the sign of the differences in column D to identify the ranked absolute differences as either negative or positive. So we'll see how that works. And luckily, we can use a couple of simple formulas to automate that. So for the negative, I'm going to go equals if, and open. Now remember what we're asking here. If this difference in column D is less than 0, which means it's negative, then in column G here, in this negative, I want to actually put the rank difference. See how we're using the sign of column D to place this rank absolute difference in column G? If it's less than 0, of course, which it are, if it's negative. And then if it's false, we're going to put nothing. So empty quotes. And then enter. So see what happened. So what we did is we duplicated this absolute sort of rank difference here into column G only if the original differences was negative. So we go to this one. We can see we have 15 moved over. That's because its original difference was negative. The next one, the difference was positive. Therefore, there's nothing there. See how that works? Now for column H, we'll do the exact opposite. So equals if the difference over here in column D is greater than 0, then we want this rank absolute difference moved over. If not, empty. And see what happens? Now we have the opposite of what we had for column G. So there should be nothing in both of these columns, G and H, if it went correctly, which everything did. Okay, so down here we need to sum those positive differences. That's our T plus. So equals sum all of our positives. And we have 211.5. So that is the sum of our positive ranks that we have over here in column F. Okay, so quickly a continuity correction. So this is equals our sum minus 0.5. And again, that's because we're using the continuous normal distribution to sort of model or approximate the discrete distribution that we're using in non-parametric statistics. So it is just minus 0.5 off the 211.5. Now for our n, we're going to use the count function, and we're going to count everything in the rank differences. Close it. And notice we have 24, and that's because we had a rank of 0, or I'm sorry, we had a difference of 0 that we deleted, and therefore we only have 24 observations. So let's go back up here to the top column here in K and do some calculations for these statistics. So T plus is what we just did down here below, so we'll just reference that. Our N is what we have here down below, we'll reference that. Now the mean is mu sub T plus, and that is the formula over here on the right. So N times quantity N plus 1 divided by 4. Now remember what we're saying with this calculation, this is what we would expect the mean to be if the negative and positive summed ranks were equal. And I'll show you the logic of that here in a second. So let's go ahead and calculate the mean mu sub T plus. So equals N, I'm going to put a parentheses there, equals N times, open parentheses, N plus 1, close all that, that's our numerator, divided by 4 equals 150. Now here's the logic of that number. Go down here to the sum of our positives. Now, if I were to do the same thing for the negatives, look what I get. Sum those up. I get 88.5. So what is 88.5 plus 211? Or to sum those up, 300. What is the middle or the median of 300? 150. See where that number comes from? So if the sum of column G and column H were the same, these would each be 150. That's what we're doing here, okay? All right, standard deviation equals square root. Now we got to keep everything straight here. So open parentheses, N times N plus 1 times 2 times N plus 1. So that's on my numerator. Close everything. Divide by 24. close everything under the square root, equals, and there is 35. So now we have our mean, our standard deviation, and our t plus. Now we can calculate our z value. That's very simple. So equals t plus minus mu sub t plus, which is our mean here, divided by standard deviation, which is right there. So our z value is 1.74286. So obviously that is positive, so that means it's in the upper end of the normal distribution. Now we want to find the p-value. And this is where it gets a little tricky, but it's not too bad. So 1.74286, if we find the p-value, let's go ahead and do that real fast. So equals norm.s.dist, or z, and we want cumulative, which is true. Enter. So notice the probability there is 0.959. That's a very large number. Well, we don't actually want that. We want the difference of that. This is telling us the probability from negative infinity all the way up to a z value of 1.74286 in the normal distribution. We want the opposite of that. We want everything to the right of 1.74286. So because we know the probability under the normal distribution is 1, we can just take everything we did there and just 1 minus that. So 1 minus norm.s.dist. Now we have the p-value of 0.04068. That's everything to the right of 1.74286. But it's two-tailed, so we need to double that. So two-tail equals 2 times that p-value, and that is 0.08136. Now remember, our alpha is going to be 0.05. So what about our hypothesis? Now we can automate our hypothesis decision. So equals, if our p-value for the two-tail is less than our alpha, then we would reject the null. Otherwise, fail to reject. Close the quotes, enter. So in this case, we fail to reject. Notice that our two-tailed p-value is greater than our alpha. Therefore, we fail to reject the null hypothesis. And in this case, what we're saying is there's no statistical evidence here to say that there's any difference in the clicks between selfie and no selfie. That is the result of our test. So let's go back to the video and finish things up. Let's summarize what we did in Excel. So mean, which is the mu sub t plus, equals 24 times the quantity of 24 plus 1, all divided by 4, and that was 150. So just a reminder, there was a difference of 0. So our original 25 observations was reduced to 24 because we had to eliminate the one that was a difference of 0. Standard deviation is 35. I'm not going to read all that out, but you can see the math. So n equals sample size of 1 differences of 0 are removed. And of course, we're using a normal approximation because our sample size is greater than or equal to 20. So the two components of our z-score are here. Our mean of our sampling distribution, mu sub t plus 150, and standard deviation. And remember, the 150 represents what we'd expect the mean to be if the ranks were equally distributed between positive and negative. So here's our test statistic and hypothesis result. So z equals t plus minus mu sub t plus over sigma sub t plus. So z equals 211.5. Remember, that was the sum of our positive ranks minus 150. That is our mu sub t plus. That is what we'd expect if the ranks were evenly distributed, positive and negative, divided by 35, which is our standard deviation. Now, we do have to apply the continuity correction factor because, again, we are using a continuous distribution to model a discrete distribution. So to do that, we just changed 211.5 to 211. It's a small change, but if you're entering answers into a homework system, if you don't do that when it expects you to, you might get that wrong. So we have 211 minus 150 divided by 35. That gives us a z-score or a z-value of 1.743. So that's going to give us the upper tail. Remember, the z of 1.743 is in the upper tail of our distribution. We want the sliver of the distribution beyond that, to the right of that. To do that, what we do is we take 1 minus the probability up to that point in our distribution. So remember, we're finding the upper slice. So the whole normal distribution equals 1. The probability is 1. And then we're going to subtract everything to the left of 1.743 to get the slice to the right of 1.743. I'll have some graphics here in a second to show you that if you're confused. So in Excel, 1 minus norm.s.dist. Then the first parameter is our z value, 1.743. True, this means cumulative. The p-value, when we do that, is 0.0407. So 0.0407. That's in the upper tail beyond 1.743. Now we have to double that because we're doing a two-tailed test. So the p-value two-tailed is 0.081. Our alpha level we chose was 0.05. So we failed to reject the null hypothesis. So our p-value is above 0.05. So there's insufficient evidence to conclude that there is a difference in thumbnail clicks between those with a selfie and ones without a selfie. And now Chloe has the results of her A/B test. So as I said, if you were confused about the z-value and probability, here are a couple of visuals to help you with that. So when we found the upper tail of our normal distribution, this is what we found. Remember, our value is 1.743. The probability there in the pink color is 0.0407. So we found that slice in the upper right, because what we did is we took 1, which is the entire curve, we subtracted out the white part to give us the part there in the pink. And then we doubled it to get the two-tailed is there. Now, because our alpha was 0.05, we were actually looking at the 95% confidence interval. Now that is represented by the two vertical lines close to plus and minus 2. So what we were looking for, if we were going to reject our null hypothesis, our areas would be beyond those two lines further into the tails. So that is what we're looking at visually. So that wraps up this video on the Wilcoxon Signed Rank Test, a paired measurement in non-parametric methods or non-parametric statistics. So remember, in parametric statistics, the comparable test is the paired t-test, where we're looking at the same person, we're looking at the same student, looking at the same whatever over two measurements. So in this case, we were looking at thumbnails, or we may have like before and after of a weight loss program or a test or something. So the paired sample t-test in parametric statistics is the Wilcoxon Signed Rank Test in non-parametric methods. So again, in this video and this topic, we don't have to make any assumption about the data being normally distributed. So as long as the differences are symmetrical, which most of the time that assumption will be met. So I hope you enjoyed this video and found it insightful. I thank you for spending your valuable time with me, and I look forward to seeing you again in the next video. Take care. Bye-bye.